Dear viewers of Akshay.com, by Vetti from Pondicherry. Good evening. Today I am going to discuss another most important chapter, alkynes. What are alkynes? Alkynes are also unsaturated hydrocarbons containing at least one triple bond. Alkynes have general formula CnH2n. This is the most important information regarding alkynes. What are the topics to be studied under these alkynes? As usual, as in the case of alkane and alkynes, classification number 1, number 2 naming, number 3 isomerism, number 4 preparations, number 5 properties, and number 6 uses. Let me discuss one by one. First, let me concentrate on classifications. Alkynes can be broadly classified into open chain compounds and closed chain compound, but remember, closed chain is not possible in the case of alkynes. In the case of alkane and alkene it is possible, but in the case of alkyne it is not possible. This is the most important information. So under the open chain compounds we have specific example acetylene and then corresponding propyne. So this is the specific example. Okay, let me come for nomenclature. Next, let me concentrate. As you know already, under the nomenclature, as usual, we have to discuss common name and IUPAC. Common name, we know there are 3 ways we can discuss. One is based on the source, based on the nature of chain, and based on the nature of the functional position of the functional groups. So here, position of the functional group is not suitable here, as in the case of alkene. So let me discuss only 2. First, based on the source and based on the nature of carbon chain. So under this common name, specific example, this is CH triple bond CH, common name acetylene. Then CH triple bond CCH3 methyl acetylene, common name. Then both sides CH3C triple bond CCH3, this is dimethyl acetylene. This is the specific example for common name. Now let me go for common name based on the corresponding chain. We have discussed already normal, iso and neo is the specific examples of the correspondingly common name. In this case, kindly follow common name I am giving for N-pentyne, CH3, CH2, CH2C, triple bond CH. So this we can give common name N-pentyne, normal chain. So this is branch chain I am giving, that is CH3, CH3C triple bond CH. It is called isopentine. This is again common name, but this common name based on the nature of the carbon chain. This is again. So let me concentrate. Next is IUPAC name. As you know, IUPAC is nothing but International Union of Pure and Applied Chemistry. So now let me discuss 1 or 2 examples under this. The first one, CH triple bond CH, common name acetylene, and the IUPAC name ethyne. The same way here, CH triple bond CCH3, the common name, that is the propyne, here that is the propylene, this is the IUPAC propyne. So another example, CH3C triple bond CCH3, it is nothing but butene or butine, 2-butine we can call it as, this is IUPAC name. Okay, let me come for the next example. So under the again IUPAC, I want to give 1 or 2 examples. Here we have complicated structure. CH3, CH2, CH2, C triple bond CH. It is 1-pentyne. Numbering is 1, 2, 3, 4, 5. 1-pentyne. The same way, here in this specific example, I will call it again 1, 2, 3, 4, 5. It is 4-methyl 1-pentyne. This is the IUPAC. So here we have to give importance for the position of the triple bond. That's why this specific example I have taken. Okay, let me go for the isomerism. What is isomerism? We have discussed already. Compounds having same molecular formula but different physical and chemical properties are called isomers, and the phenomenon exhibited by this isomer is called isomerism. And this isomerism we can broadly classify into 2 types. One is structural isomerism, another is stereo. Structural we can broadly classify into 4 types: chain, positional, functional group, metamerism. And stereoisomerism broadly we can classify into 2: optical and geometrical. So totally 6 isomerism possible. Out of 6 isomerisms, in the case of alkyne, only 3 isomerisms are possible. One is chain isomerism possible, positional isomerism possible, and optical isomerism possible. Kindly follow, my dear students. So, when questions are asked on the competitive examination, so one among the following isomerism is possible, one among the following isomerism is not possible. So, based on this, they are asking questions. So, these 3 are possible. What are the other 3 not possible? That is, kindly follow. The functional group isomerism is not possible, metamerism not possible, and geometrical isomerism not possible. So, if you have this idea, any question you can answer under the competition point of view. Okay. So, under this first one, let me take a chain isomerism. What is chain isomerism? Compounds having same molecular formula but difference in the arrangement of carbon chain are called chain isomer, and the phenomenon exhibited by the chain isomer is called chain isomerism. A specific example here I am giving N-pentine and isopentine. This is a common name. N-pentine, 5 carbon atom. So this is again 5 carbon atom isopentine. Or specifically, if you want to give IUPAC name, this is 1-pentine. 1-pentine is the IUPAC name. The corresponding this is 3-methyl, that is 1-butyl. This is the IUPAC name for this. The idea here is, this is the normal chain, this is the branch chain. So this is an examples of chain isomerism for alkynes. Okay, let me discuss next type. It is positional isomerism. What is the definition for positional isomerism? Compound having same molecular formula but difference in position of the functional groups. They are called positional isomers, and the phenomenon exhibited by this positional isomer is called positional isomerism. Specific example, 1-pentine and 2-pentine are specific example having the same molecular formula. So here 1, 2, 3, 4, 5 carbon atom. The carbon of the triple bond is connected to the first carbon atom, so we are calling it as 1-pentine. In this case 1, 2, 3, 4, 5. So the position now changes from 1 to 2. That's why this is called as 2-pentine. So 1-pentine and 2-pentine are specific example for positional isomerism. Okay, let me go for the next one, type 3, that is optical isomerism. What is optical isomerism? Compounds having same molecular formula but difference in optical activity are called optical isomers, and the phenomenon exhibited by this optical isomer is called optical isomerism. Kindly students, kindly follow, just listen me. So I am giving one important information. Normally it will not be given in books. Out of 6 isomerism possible in all organic compounds, chain isomerism is possible in all types. This is the number 1 important point you have to keep it in mind. Number 2, optical isomerism is always possible in all types of compound depending upon the nature. So this is the most important information. Okay, so let me repeat again. Compounds having same molecular formula but difference in optical activity are called optical isomers, and the phenomenon exhibited by this optical isomer is called optical isomerism. So specific example here, 3-methyl 1-pentine exists in 2 forms. It shows optical activity because this is having an asymmetric carbon. As you know already, optical activity arises in 2 ways. One is due to asymmetric, another is due to dissymmetric. So this is an asymmetric compound containing, so here just see ethyl group, hydrogen, and C triple bond CH. So 4 different groups. So central carbon is asymmetric. So one asymmetric carbon means it will exist in 2 forms. So kindly see the structure here. So this is the structure. So 3-methyl 1-pentine exists in 2 forms. One is R form, another is S form. This we know according to Kahn, Gold and Perlock's rule. So we can give R and S configuration that you have already know. So this is the corresponding R 3-methyl 1-pentine. This is S 3-methyl 1-pentine. So same compounds. Compounds having same molecular formula. So one will rotate clockwise, another will rotate anti-clockwise. That's why this is called optical. It shows optical isomerism. This is the most important information regarding the isomerism. Okay, let me go for the next subtopic, preparations. Preparation of alkynes. So, if you refer your textbook, whether it's a Samachira or CBSE books, that is only a limited number of given, the methods are given. So, I am giving a systematic order so that any competitive examination, in any All India competitive examination, you can go without any fear. So, let me start this way. So number 1, from lower alkynes. That means alkyne, from lower alkene I can prepare any higher alkane. This is the most important method. Conversion of lower member to higher member. Specific example here, acetylene contain only 2 carbon atom. So let me treat with sodium. So in presence of liquid ammonia, so I am getting sodium derivative of that particular recipe. This is called sodium acetylene. Why this is sodium substituting? Because the hydrogen is acidic in nature, that will be replaced by sodium. So then when you treat with 1 mole of methyl iodide, we are getting a higher number. So from lower member to higher member we can prepare. This is the most important method. Normally interconversion, the question can be asked under this. Normally in IIT this type of question will be asked. So this is one method. From lower member I can prepare higher member. Now in this case, just I want to give one more information, kindly follow me. Acetylene or terminal alkynes can be converted into metal acetylides or metal alkynides by treating with sodium and liquid ammonia, and these derivatives upon the reaction with alkyl halide give substituted alkynes. Why this point is most important? Because suppose if the alkane is not having terminal hydrogen, this method is not suitable. That is the most important information. So to convert lower member to higher member, you must have an acetylene, that is alkynes should have a terminal CH. That is the most important condition. If it is not having a terminal CH, you cannot convert. So that is the first condition. And the another important point you must have here, alkylation of alkynes can also be accomplished by treating with a suitable Kriegner reagent. As you know, Kriegner reagent, general formula RMGX is coming under the alkyl halides. We will be studying later. So this Kriegner reagent, suitable Kriegner if you use, followed by action of an alkyl halide, again you can prepare for lower member to higher member. So let me say a specific example. RC triple bond CH, when you treat with methyl magnesium iodide, this is the intermediate form. Then again you treat 1 more methyl iodide, the corresponding higher member of alkyne you can prepare. So this is the most important information. Anyhow, the most important condition is the lower alkyne should have an acidic hydrogen. Then only the conversion of lower member to higher member it is possible. This is the most important point you must have. Normally it will not be given in the book. Okay. Next one, second method. From alkyl halides I can prepare. So first from lower member to higher member. The second method is from alkyl halides. So here let us take example. Here general method I am giving. From 1, 2 dihalides. 1, 2 dihalide means this is called vicinal dihalide. Kindly follow, this is the most important. Halides they can classify in 2 ways. One is vicinal dihalide, another is gem dihalide. Gem means 2 halogen atoms are present in the same carbon atom. Vicinal means it is present in the neighboring carbon atom. This is 1, 2 vicinal. So the general method here, RCHEX, CH2CX. So this is the general compound. When you treat with alcoholic AOH, the corresponding elimination reaction takes place. So we are getting this one. The RC triple bond CH is formed to KX and this 2. This is general. So specific example I will give now. So I am taking 1, 2 dibromoethane and I treat with alcoholic AOH, I am getting acetylene and the corresponding potassium bromide and water. This is specific example. So I can prepare acetylene from corresponding 1, 2 dibromoethane. The same way here. Another example, the next member. 1, 2 dibromopropane. This is 1, 2 dibromopropane. So same way, when I treat with alcoholic AOH, I am getting a next member propane. The most interesting information here it is a elimination reaction. Specifically, it is dehydrohalogenation. That is the most important. So along with the alkynes, so KBr and water is always produced in this particular reaction. This is the important point you must take. Okay, let me go for the next one. Same halide. Now instead of 1, 2, this is 1, 1. I already pointed out this is gem dihalide. So that both halides are present in the same carbon atom. So in this case, we will call the name reaction as dehydrohalogenation. Removal of halogen. Kindly follow a general method here. RCH2CHPr2 general. When you treat with alcoholic AOH, it is the eliminating reagent. So RC triple bond CH, it is a compound is formed. Alkyne, K2 KBr and H2O. Now specific method under this, let me take now 1, 1 dibromoethane. This is the compound. 1, 1 dibromoethane. On treatment with the alcoholic AOH, the corresponding acetylene is formed along with the KBr and water is formed. This is another most important. So either from gem halide or from within a halide, dihalide, we can prepare corresponding alkyne. Another general method here 1,1, 2,2 tetrahalide also we can prepare alkynes. This is the general RCXX, CXXH. When you treat with zinc in presence of alcohol, again the elimination reaction takes place. We are getting corresponding alkyne. The interesting information: the first case we are using alcoholic AOH. In this case, we are using zinc. This is the most important. Kindly follow. This is the most important difference between these two types of reaction. Okay, let me give you a specific reaction under this. So here it is 1,1, 2,2 tetrabromoprofane. This is the name of the compound. Let me repeat again. 1,1, 2,2 tetrabromopropane. On treatment with zinc in presence of alcohol, we are getting propyne. Along with zinc bromide is forming. This is called debromination reaction specifically. This is the interesting information under this. Okay, let me go for the next method. So third method is from salts of unsaturated dicarboxylic acid also we can prepare alkynes. So what is the salts of unsaturated dicarboxylic acid? We have now this, let me give an example. This is COH. This is an unsaturated acid. We will call it as, this we can exist in two forms. One is fumaric acid, another is malic acid. So same side malic acid, opposite side fumaric acid. So in this case, potassium salt. So when you take this salt and if you pass electric current, it's called the electrolysis, the corresponding acetylene is formed along with the carbon dioxide, potassium hydroxide and hydrogen. This is another important method. So from the unsaturated acid salt, we can prepare the corresponding alkyne. This is another most important method we can prepare. So I have discussed all the method commonly available to prepare alkyne. I have discussed. So let me concentrate now coming for properties. As you know, properties we can discuss under the physical properties. Another is chemical properties. So coming for the physical properties, number one, alkynes are insoluble in water but soluble in organic solvent. That's the first one. Second property, generally first three members are gases, next few members are liquids, and the higher members are solid. This is general for all hydrocarbon and all other compounds. Number three, they are lighter than water. Generally, alkynes are lighter than water. And four, the physical properties increases with increasing molecular weight. That is, boiling point, melting point increases with increasing molecular weight. This is another most important physical properties. Okay, let me concentrate on chemical properties. Under the chemical properties, I can classify a number of ways. So first let me take formation of alkanes. So under this heading, I am going to discuss how we can prepare alkane from alkynes. The specific reaction for this one is catalytic hydrogenation, or another name is addition of hydrogen. So that means by taking alkynes, I will pass hydrogen in presence of suitable catalyst, I will get corresponding alkanes. Okay, alkynes undergo addition reaction with hydrogen in presence of metal catalysts like nickel, platinum or palladium to give saturated alkanes. Specific example I will show you now. So this is general RC triple bond CH, 2 moles of H2 in presence of nickel catalyst and phosphorus. So I am getting RCH2CH3. So 4 hydrogen atoms added and we are getting alkane. So specific example, acetylene. So passing 2 moles of hydrogen in presence of nickel and phosphorus, I am getting ethane. Another member, higher member, propyne. So by taking propyne, by passing 2 moles of H2 gas in presence of nickel and phosphorus, I am getting propane. So any alkyne, if I take and pass hydrogen, I will get corresponding alkane. This is the very easiest method of preparation of alkane from alkyne. Okay, the second method, formation of alkane. This is the most important method, kindly students, you should know, because your books is not containing this. Because often questions are asked based on this, competitive questions. That is addition of hydrogen, but we are not converting alkyne to alkane, but we are stopping at the alkene. So special catalyst we are using, that's called a Lindler's catalyst. So competitively they will ask questions, what is Lindler catalyst they will ask. Or sometimes they will give the catalyst and give the product. So here, alkynes undergo additional reaction with the Lindler catalyst to form alkene with the cis isomer exclusively. This is the most important information. So here I can use the term, two terms I can use here. One is stereoselective, another is stereospecific. Commonly, often this question is asked under the IIT question papers, we can see. What is the stereoselective and stereospecific? Let me explain. When you say stereo means stereoisomerism of two types. One is optical, another is geometrical. Geometrical means, as you know already, it is cis and trans. This is the geometrical isomer, cis and trans. Suppose when we are starting with one reagent and we are getting the mixture of two products, say for example in the case of optical, plus as well as minus. So one is major, another is minor. That particular reaction is called stereoselective reactions. The same way, if I am starting an experiment, if I am doing an elimination reaction, one is cis, another is trans, and one of them, the cis is major and trans is minor, mean that particular reaction I call it as stereoselective reactions. Then you can raise a question, what is stereospecific? So when we are using a special catalyst, selectively only one product will form. That we'll call it as stereospecific. So stereospecific reaction is one in which only one product will form, even though there are two possibilities. So in this, suppose in the case of optical, so only plus or only minus, we'll call it as stereospecific. Same in the case of geometrical isomerism, only cis or only trans, we'll call it as stereospecific. Okay, with this idea, let me go here. So first case, this is 2-butyne, specific example. On reduction, in presence of palladium, barium sulfate and sulfuric acid, we are getting only one product, cis-2-butene. That means both hydrogens are added from the same side, cis addition. So cis-2-butene, this is stereospecific. This is the important information. So stereospecific, the catalyst is palladium, barium sulfate and sulfuric acid. Coming for the another example, this is again 2-butyne, but instead of palladium, barium sulfate, sulfuric acid, if you use sodium and liquid ammonia, now instead of cis, we are getting trans-2-butane. This is another isomer, that is a geometrical isomer, trans isomer, trans-2-butane. So it is the both hydrogen will be added in the opposite side. So again, this is a stereospecific reaction. So this is the most important information question can be asked. So by giving the reagents, they will ask the product, or by giving the starting material and the reagent, they will ask the product. So you should be very careful under this. Okay, let me go for the next one. Formation of tetrahalide, halides. Under this, addition of halides, I will discuss. General methods. RC triple bond CX. When you add X to X to maybe F2, CL2, Br2 or I2. So the corresponding product will be RCX double bond CX CH. A further addition, one more. Again, I am giving tetrahalo RCXX CXXH. So this is the general. So specific example, let me discuss. Then you can understand. Under the specific, let me take acetylene, and if I pass first chlorine, one more, I am getting 1,2 dichloroethene. Here dichloroethylene it is. Further addition again, I am getting a tetrachloro. So it is nothing but 1, this is 2. So 1, 1, 2, 2, tetrachloroethane. This is the interesting information. So this is taking place, addition of halogens. Okay, let me go for the next one. This is formation of halogen compound. So under the addition of hydrogen halide, next let me discuss addition of hydrogen halide or hydrohalogenation. Right, alkynes undergo addition reactions with hydrogen halide to form dihaloalkane. This is the most important. Dihaloalkane. So here the most important information is, depending upon the position of the triple bond, the halogen formation may be different. So just see here, specific example. So general method I am giving now, RC triple bond CH. When I treat with the HX may be HF, HBr, HCl, HI. So the product will be, so how it will be cleaved? It will be cleaved in the form of H plus, X minus. So here it will be cleaved in the form of plus and minus. So here plus means the minus will come here, plus will come here. This is the product. RCX, correspondingly double bond CH2. If I add, because still unsaturation is there, if I add one more mole of HX, again I am getting RCX2CH3. This is the general. So let me take a specific, you can understand this. So let me take again acetylene. When I add one mole of HBr, I am getting 1 bromoethene. Suppose I will add one more excess, then correspondingly 1 dibromoethane. Kindly follow, this is gem dihalate compound. 1 dibromoethane. This is the compound. Okay, let me come for here. Propine. When I treat with HBr, the first product will be 2 bromoethane. One more, if I add HBr, this is nothing but 2, 2 dibromopropane. This is the interesting. So dihalogen, both halogen atom are added in the same carbon atom. This is the preparation of gem dihalide. This is the most important information under the addition of halogen halides. The next most important information is formation of aldehydes and ketones properties. So we can prepare aldehyde and ketone by using corresponding alkynes by suitable reagent. So under this, let me discuss addition of water. So let me explain what way when I add water, aldehyde and ketones are formed. I will explain. When alkynes are passed through dilute sulfuric acid in presence of mercury sulfate and 60 degrees centigrade, the corresponding aldehydes or ketones are formed. So depending upon the nature of alkyne, it may be an aldehyde, it may be a ketone. Let me give a specific example, then you can understand. So this is general, RC triple bond CH, water, dilute sulfuric acid, mercury sulfate. That is what way it will cleave now. Water will cleave like this. H plus and OH minus is again will be added there. So this is the intermediate form. And from this intermediate, will rearrange to give this compound RCOCH3. Suppose if R is CH corresponding aldehyde, R is CH3 corresponding ketone. So take now specific example, acetylene. So when I add water again cleave, so positive and negative part, this is the intermediate form. So this H will migrate here correspondingly to produce corresponding acetaldehyde. So the ethyl, that is acetylene, on addition of 1 mole of water in presence of dilute sulfuric acid and mercury sulfate, I am getting acetaldehyde. Suppose instead of acetylene, if I use propylene with the propyne, the corresponding when I add water in presence of dilute sulfuric acid and mercury sulfate. So now this is the intermediate and this is rearranged to give acetone. Kindly follow. So now you can easily understand, if R equal to H means the corresponding acetaldehyde, R equal to CH3 means it is acetone. This is the important information. Often question asked only from this, they are asking question, kindly have it in mind. So addition of water. Now, next one, formation of dihaldehydes, or that is dihaloaldehydes or ketones. This is another interesting information, or simply under this, addition of hypohalous acid, that is HOX, HOCl, HOBr, HOI, anything that we can. If I add this, what will happen? The most important information, this is normally students we can do mistakes. So what way it will cleave? HOX will cleave in the form of, that is OH minus and X plus. This is the most important. So why I am giving caution here? Because X normally whenever halogen atom it will be minus. But in this specific example, X is not a minus, it is plus. Only OH is minus. That you can see here. In this case, so HOX will be cleaved in the form of OH minus X plus. So it is an intermediate. From this we are getting again one more. We are getting this product. Our rearrangement, this is the product. So let me give a specific example, you can understand. So acetylene, I am adding HOCl, the hypochlorite. So when I add this, what will happen now? So as usual, this is OH minus Cl plus. So this will you can add here. So OH one side, Cl another side. So what is this is now undergoing correspondingly. I will add one more molecule. The correspondingly CHO, CHCl2 it is formed. Dichloroacetaldehyde it is formed. Here again HOCl. The first intermediate this is forming OH one side and the Cl is another side. One more molecule if I add now, again the correspondingly intermediate form, two OH groups on the same carbon atom. From that water is getting eliminated, I am getting a ketone, that is dichloroketone. Specific example is 1,1 dichloroacetone. So if I use acetylene, the final product is dichloroacetaldehyde. If I use propyne, then corresponding 1,1 dichloroacetone. Just like acetaldehyde acetone, in this case, the dichloroacetaldehyde and dichloroacetone. This is the main difference between these two. Let's go to the next. Now, another most important addition of boron hydrides. Their name reaction is called hydroboration. Alkynes, like alkenes, undergo hydroboration to form vinyl boranes, which on oxidation with alkaline hydrogen peroxide to form aldehydes and ketones, respectively. So again, we are getting aldehyde and ketone with the help of the addition of boron hydride. The general method is RC triple bond CH. When you add BH3, we are getting this intermediate. RCH double bond CH BH2. Then, in presence of H2O2, that is alkaline H2O2, so we are getting this product correspondingly. It is rearranged to give the corresponding RCH to CHO. The only important information I want to record here, BH3 it is not stable, kindly follow. Borane it is not stable because it is not having octet electrons. It is unstable. So usually it will be in the form of B2H6 diborane. So just for simplicity, I am giving now BH3. Otherwise, it is only a diborane. Okay, let me go for next one. So under this, the specific method under this, CH triple bond CH and reacts with 1 mole of BH3. So first we are getting now CH2 double bond CH BH2. Then when you treat it with alkaline hydrogen peroxide, so this we are getting the corresponding PH3 substituted by OH, which is rearranged to give acetaldehyde. The same way, if I take now propyne, so by adding one mole of PH3, I am getting this intermediate. So when that is by treated with H2O2 and OH minus, I am getting this rearranged to give correspondingly propanaldehyde. So acetylene gives acetaldehyde. Propyne gives correspondingly the propanaldehyde. This is the formation of aldehyde and ketone under this specific example. The next one, formation of diketones and diacids. Another most important information, preparation of compound from alkynes we can do. That is, I can call it as addition of ozone. What is the addition of ozone? Alkynes react with ozone to give ozonides, which get decomposed with water to yield diketones or dialdehydes. So this dialdehyde diketone further oxidation gives corresponding acids. So this is a general method. RC triple bond CH reacts with 1 mole of OH3, giving this intermediate ozonide. And in presence of water, zinc, it is giving a corresponding aldehyde, that is the RCO, CHO and zinc oxide. Diketones are aldehydes. So this is the general. Let me give a specific example. You can understand. So acetylene reacts with O3, that is ozone, in presence of zinc and hydrogen peroxide, zinc and water. I am getting this ozonide intermediate. So this ozonide that is on hydrolysis, correspondingly we are getting this CHO. The most important information is bond breaks here, bond breaks here, but it is not breaking here. That's why we are getting this clioxal. CHO. So this on oxidation hydrogen peroxide gives correspondingly formic acid, 2 moles of formic acid. This is the most important information. So same way, if I take propyne and I treat with the ozone in presence of zinc and water, so this is the intermediate ozonide. This is undergo hydrolysis to give the corresponding ketaldehyde. CH3COCHO on oxidation give acetic acid and formic acid. The interesting information is on ozonolysis, the final product in the case of acetylene is 2 moles of formic acid. In the case of propine is acetic acid and formic acid. So question can be asked based on this. Okay, let's go for the next one. The most important reaction, another property is polymerization reaction. General. So 3 moles of RC triple bond CH under pressure in presence of red hot tube undergo polymerization to produce an aromatic. Specific example I can take now correspondingly. 3 moles of acetylene under pressure in presence of red hot tube produce benzene. So benzene aromatic compound can be obtained from acetylene on polymerization in presence of red hot tube under pressure, IV pressure. Suppose instead of acetylene, if I use 3 moles of propine, same condition under pressure and red hot tube, now I am getting acetylene. That is mesitylene. That is CH3, CH3, CH3. I am getting mesitylene. This is the most important information. Kindly follow. So simple acetylene gives benzene, propine gives correspondingly mesitylene. That is nothing but 1, 3, 1, 2, 3, 4, 5, 6. 1, 3, 5 trimethyl benzene. That is mesitylene. The next one. Reactions of acidic hydrogen. The main difference between alkynes and alkene and alkyne I have already discussed. That is because the hydrogen that is present in the acidic, that is in the alkyne, is acidic in hydrogen. Suppose if alkene is having a terminal CH, that hydrogen is acidic. So this specific hydrogen, acidic hydrogen, have some important characteristic reactions. So let me discuss now. Terminal hydrogen of alkyne is acidic in nature. When acetylene is passed into ammoniacal silver nitrate solution, silver acetylide, a white precipitate is formed. That is a white precipitate is formed. That is silver acetylene is precipitated. What is the reaction? CH triple bond CH. When you treat with silver nitrate in presence of ammonium hydroxide, the both sides hydrogen will be substituted by silver. It is called silver acetylide. It is a white precipitate. So this is the most important information. So in the case of acetylene, when you treat with ammoniacal silver nitrate, you have silver white precipitate, silver acetylide is formed. Suppose when acetylene is passed into ammoniacal the cuprous chloride solution, a red precipitate is formed. That is the another interesting information. Can you see the reaction? So in this case, acetylene, we are treating Cu2Cl2 in presence of ammonium hydroxide. So what will happen now? Copper acetylide is formed. That means that these 2 hydrogen will be substituted by 2 copper. So the name of the compound is copper acetylide. It is a red precipitate. This is the another interesting information. So what is the importance of this reaction? This reaction is used to differentiate terminal hydrogen containing alkyne from non-terminal alkynes, and also from alkenes and alkane we can be able to differentiate. This is the most important information I want to record here. Next one. Coming for uses of alkynes, the final subtopic. Number 1. Acetylene is used as a starting material for manufacture of many industrially important compounds like acetaldehyde, acetone and benzene. Number 2. Acetylene is used in oxyacetylene flame for welding and cutting metals. Next one. Number 3. Acetylene is used as a solvent in the form of tetrachloride derivative of acetylene. Number 4. Acetylene is used as a starting material for the manufacture of PVC, synthetic rubber, etc. I hope you have enjoyed the lecture. Thank you.